All right, we are back. Welcome to section 6.2, one-to-one functions, inverse functions. So personally, I find it a little strange the author's bringing this up now because there was a chapter on functions. Do you remember chapter 2 where the author talked about functions? He didn't talk about whether functions were one-to-one back there, didn't talk about inverse functions. But I don't know, actually in a way he did. In other words, it's kind of hard to talk about functions without talking about functions that have this property of being one-to-one functions, because most functions do. And you already have an intuitive understanding of inverse functions, actually, from what we've done already. So I don't know how much, there'll be some new material here, but I certainly don't know why it's wasn't mentioned earlier. I do know why it's mentioned now, though, and that is the author wants to talk about exponential and logarithmic functions. And the exponential function is one-to-one. So is the logarithm function. And they're inverses of each other. So if you have y equals a to the x and log base a of x, these are functions the book hasn't really talked about yet, but because that comes later in chapter 6. But these two functions are inverses of each other in the same way and the same properties where x cubed and cube root of x are inverses of each other. Depending on how far you want to take that idea, some books actually take that really far, the idea of inverse functions, to the point where I don't know, some students can't really recognize the logarithm function without thinking the exponential function and then doing whatever inverse. I don't know. Kind of hard to talk about that without getting there, but before we get there. But in any case, it's a fairly long section with lots of, two major topics. But the questions themselves transcend chapter 6. Determine whether a function is one-to-one. Verify find the inverse, verify the inverse. All right. So our definition, is saying this: a function is one-to-one if I take two different numbers. Now they call them x1 and x2. So put in x1 and x2, and they're not equal to each other. But if I put x1 and x2, the function's one-to-one if it gives me a y1 and a y2 that are also not equal. It gives me a different number. In other words, you put a different number in, you get a different number out. Then it's one-to-one. So one of our favorite functions, y equals x squared, is not one-to-one. Why? Because if I were to put in -2 and +2, in both cases I get 4, not a one-to-one function. We'll see better reasons why it's not a one-to-one function, but that's our definition. Not a fan of these little arrow things. If you find something there worth looking at, that's fine, but let's look at this particular problem. And one of the things I have to warn you about is functions can be presented to us in more than one way. They aren't always presented to us, like y equals x cubed. That would be an equation. They can be presented to us as a list of ordered pairs, a table. I haven't finished this table, but let me go ahead and do that. If I consider this point A, point B, point C, point D, point E, this -3, 5 would be, if you put in -3, you get 5. If you put in -2, you get 3. Now this looks like this particular problem. It's not random. The author certainly did do some calculations here. Or at least I'm saying he did. In other words, there is an equation related, that would do this. I'm not going to even try to find it right now. It's not the point. point is, if I take this and look at it, notice how all the x's are different, and at no point did I get a repeated y value. So this is 1 to 1. Now I can do it one better than that. If I were to plot these points, -3, 5, there's point A, we'll call it, -2, 3, not doing a really good job plotting this, but -3, there's point C, point D, 0, -1, and point E is 1, -3. All right, so there are the points. Kind of looks like this is a line, and I think we'd be correct in assuming it probably came from there. But when you're given a table, when you're given a list, don't make assumptions. In other words, don't assume that you know what would happen if you put a 2 in here. You know, we weren't given that on the list. Oh, we were. 2, -3. Yeah. I just noticed that. They skipped 1. This was 2. All right. Guess I did it right. We don't know what would happen if we put a 1 in here. We probably do. In other words, we could kind of mess with it and figure out the pattern, but that's not our job. Our job is, if you have a table, you have an input and an output. We're not, in this case anyhow, trying to figure out what the pattern is. All we're trying to do is determine, is this a 1 to 1 function? And we're about to find out from this picture, with or without the line added. Let me take that line out of there. This series of dots, I didn't mean to erase everything. That series of dots, is that a 1 to 1 function? And sometimes the image is the best way to tell if a function is or is not 1 to 1. Get this a little more accurate. Okay. And why is that? Well, if you have the graph, you can run something called the horizontal line test. So keep in mind, you can have an equation, you can have a table, which is closely related to the list, and you can have a graph. And most of our work in an algebra class is switching between one and the other. In other words, you're given the equation and you want to graph it, or you're given the equation, you make a table, and from the table you plot points and you graph it. And, as we saw in Chapter 5, sometimes the other way around, they give you the graph and you want to find the equation, or they give you properties. You get the idea. All right, well, graph is probably the best way, most visual way anyhow, to tell if a function is 1 to 1, because there's something called the horizontal line test. If a horizontal line intersects it more than once, it's not 1 to 1. So the basic idea is, let's look. If you have a function that does this, right, has a turning point like this, it's not going to be 1 to 1, because horizontal lines, even if it's just one horizontal line, but there exists a horizontal line that will intersect it and it will give you 2 points, not 1 to 1. This one, y equals x to the 5th, is 1 to 1 because every horizontal line intersects it one time. One time. You intersect it once. This one intersects it once. 1 to 1. There's no coincidence that 1, intersecting it once is part of the name. They got to throw this at us. This isn't proof that, well, this isn't required for every function, but every 1 to 1 function, but a function that is increasing is 1 to 1. And if the function is decreasing on an interval, it's 1 to 1. So remember that y equals x to the 6th. We don't say this is increasing, right? We say it's decreasing until the turning point, then it's increasing, because we read it from left to right. Not 1 to 1. It wasn't increasing and decreasing on the entirety of its graph. It switched from decreasing to increasing. But y equals x cubed, as this graph, and I know the arrow's pointing down, but if there's an ant walking on this figure going from left to right, the ant's increasing and it's continually increasing. If the graph is increasing then the entire time, it's 1 to 1. That's our shortcut. I don't know. It's one more shortcut to tell you if a function's 1 to 1. So here's some notation. All right. So if a function is 1 to 1, we call it f of x, and it will have an inverse function, and our notation for that is the inverse, f inverse x. So a function will have an inverse function. A 1 to 1 function will have an inverse function. I talked a moment ago about graphs being functions being, you can graph a function. Well, if you do graph a function and its inverse, this will happen. They will be symmetrical with respect to the line y equals x. So I actually think about that with just a point. Let's say this point is 1, 5. And I'm going to call it A. Well, there's another point on the other side of 1, 5, which I'm going to call A inverse. And what's interesting about this is I can predict what the ordered pair is going to be. It's going to be 5, 1, just switching the x and y around. If you switch the x and y around, you get this inverse point. And so one of the key ideas that I'm going to keep on talking about is switching x and y when we're talking about inverse functions. So the whole thing about 1 to 1 functions was just to tell you that if a function is 1 to 1, it has an inverse. And if it's not 1 to 1, well, it doesn't have an inverse unless you make it 1 to 1. All right, so they have this example where they just kind of, they generously provided you with the line y equals x, and they're going to ask you to do what I did. Switch x and y. Switch the x and y. It'll take this point, I'll call it A, and make it A inverse. This point, 1, 0, is now 0, 1. So if this is B, this is B inverse. If that's C, switching them would give you the same thing. So C and C inverse are the same points. If I connect those together, I will get the graph of the inverse function. So you can see what they did. Right? The original function, that's switching the x and y, you automatically get a function that is a mirror image of that function if the mirror is the line y equals x. Now I got to tell you, this whole thing looks a lot different than the line y equals x isn't provided or isn't there. And it's not like it's automatically there, this line y equals x. We draw the x-axis and the y-axis, but we don't generally draw this little line here. So this might be interesting, other ways to talk about it, but the domain of f is the range of the inverse. The range of f is the domain of the inverse, and that might be interesting to us later, or might not. I'm not really sure how interesting this fact is, because in practice, this is a little easier to see when you're actually doing the problem. But you should be prepared to answer questions about it. Again, in practice, so much easier than this. So just get past that. All right. To verify two functions are inverse. Now, we actually have already done this without knowing it. To verify two functions are inverse functions, you do the composition of those functions, g of x. And they're not using the composition notation. They just went straight to, G inverse of G of X. But you do the composition, and if you do the composition and you get X, meaning that these canceled and you just get X, then you've just verified that they're inverses. So what are inverses? G of X equals X to the 5, and G inverse equals a fifth root of X. They did it the other way around. It doesn't really matter which way you do it. If you do it the other way around with G on the outside, in other words, that is G of G inverse. If you do that and you get X, that's also proof that they are inverse functions. So verifying inverse functions means you go through this process, you get X on the outside, you get to say bingo because you learned something that you didn't know before. They did it with F and F inverse, where F of X was, 1/4 X plus 7. That was one of the functions, and the other function was 4x minus 7. And again, you should smell inverse here. Kind of looks like they might be a candidate for inverses because one has a minus 7, one has a plus 7, one has a, multiply by 4, the other has a multiply by 1/4. The thing is, if the parentheses were different in any step here, they would not be inverse functions. So parentheses, order of operations, all that's important. So it's worthwhile to run through this test, and if you get X on the outside, meaning everything canceled, all the numbers canceled, and you're just left with X, then you've verified that they are inverse functions. Another one, they're all pretty much the same. Find the composition of the functions, and do you get X? They did talk about domain, and I suppose I should mention this. So look at the process and notice the one moment where you have a division that you have to stop and calibrate, right? You have to say, you know what? X cannot equal -2 because I'd be dividing by 0. Obviously, if I put negative, I could put anything into X. But they're saying, you know what? Technically speaking, let's look at this equality right here. These aren't really equal because one of them gives you an error in your calculator and one of them doesn't. And so you just have to exclude when it doesn't work. Same thing we've been doing before. They went through the process, but notice the restriction. Finding the inverse of a function defined by an equation. Yeah, I'm going to pause this because it's a pretty big deal right here. So I'll pause this one, and we'll pick up on the next video. So just review where we are here. So I'm coming back, but this is section 6.2, and there'll be a part 2 to this.